I can start? Okay. I just put the integral back because we still need to work on this today. So we had the hard region in this integral. The result is not anymore there, but you have it in the notes. By the way, before I forget it, I should say that on the very first page of my notes, and I also gave this to the organizers earlier, you see a list of references. And in particular, it contains a book on soft-collinear effective theory written by Thomas Becher and company. And this book is freely available on the archive, so you can just download it. And in particular, on the method of regions, you will find numerous examples which are actually simpler than the example I'm discussing here. So this is a very good source. It's free, it's on the archive. Once you're back home, just take a look there to get a little bit more familiar with this technology. So this was our integral. We did the hard region. It was not so difficult to do it. We found a result that is a bit puzzling with a double pole, double logs, single logs of mu square over q square. We're now going to continue to do more regions. And the question is, what regions should we look at? Remember, this was the integral. We considered gluon exchange between two quarks. This quark is collinear. This quark is anti-collinear. And at the moment, we looked at the case where the gluon momentum was hard. Now, of course, if you have this topology, a natural region to look for is that you say, well, what if this gluon momentum is somehow aligned with the jet that goes in one direction or aligned with the jet in the other direction? Okay, so the next regions we're going to look at is the case where K is collinear or anti-collinear. And you also notice that the problem is completely symmetric with regard to collinear or anti-collinear, right? I'm just changing the sign of the C component. So we'll just study this in detail, and then the anti-collinear will be identical. So once again, we need to expand these two propagators in a certain region assumed for the loop momentum. So if the loop momentum is collinear, we know that the loop momentum scales like lambda square 1 lambda, right? So with this scaling, lambda square 1 lambda, where this is n dot k, this is n bar dot k, this is k square perp, and this is all in powers of q. So let's start again with this momentum, k plus p1. K plus P1, K is collinear and P1 is collinear, so K plus P1 is also a collinear momentum. And then there is nothing to expand out. Okay, if I write this in light cone components, it's n dot K plus P1, n bar dot K plus P1 plus K plus P1 perp squared. This is the small component, this is lambda squared. This is the big component, which is 1. And this is the perp component squared. And you see all terms in this sum are of order lambda squared. So there's nothing to expand out. Nothing to expand. However, for the second momentum, this will not be the case. K plus P2 squared. Again, let me write it out like here. This is K square plus 2 K dot P2 plus P2 squared. K square is of order lambda square. P2 square is also of order lambda square. 2 K dot P2 I can write as n dot K n bar dot P2 plus n bar dot K n dot P2 plus 2 K perp P2 perp n dot k, since it's a collinear momentum, is of order lambda square. N bar dot P2, do you remember P2 was anti-collinear? N bar dot P2, is it the large or the small component? Small component, great. So it's also of order lambda square. So you see this term is of order lambda to the 4, I can drop it. N bar dot k is order 1. N dot P2 is order 1. It's the large component of the anticollinear momentum. So wow, we get an order 1 term. So actually I can also drop this k square because this is order lambda square. Okay? And here this is lambda, this is lambda, this is also lambda square, so I can drop it. So you see, to first order, this becomes really interesting. This is simply n bar dot k n dot p2. And if you wish, using the notation we had earlier, you can write this as 2k dot p2 plus. So you see, we get a new integral now in the collinear region. Which is now this stupid prefactor. Always need to write it down. So we get a new integral now. The first propagator stays as it is, k squared 2 plus I0. The second one also stays as it is, k plus p2 squared plus I0. The third one now is different. 2k dot p2 plus I0. And upstairs it's q squared. So here we find a linear propagator, linear in loop momentum. Actually, linear propagators are not uncommon in effective theories. In HQET, you remember that the heavy quark propagator was linear in the residual momentum. So loops in HQET are also linear in loop momentum. Now, if you want to evaluate this integral, you need a little bit a different Feynman parameter representation, because if you just use standard Feynman parameters, normally each term has a k square and the sum of all Feynman parameters is equal to 1. This wouldn't work here. On the homework, on the exercise sheet, I give you the relevant master integral to do this type of integral. And in fact, I think the second problem on the homework is to evaluate this integral. So I'll just leave it to you. What you find, or what you should find, is the following expression. Minus 1 over epsilon square. So again, we get double poles. Oh, by the way, I made a mistake here. Sorry, this is 1. Yeah, you can ask, what can this integral depend on? Okay, so in the integrands we have p1, so it can depend on p1 squared, obviously, which was our variable p1 square, which is minus p little 1 square. P2 plus, remember, is a light vector. If we square it, we get 0. So the only other thing it can depend upon is P1 times P2 plus. And this is 1/2 q squared. So in the end, this loop integral can depend on q and P1 squared. This is the only variables. But actually, what you find is that the dependence on q is trivial. The dependence on q is simply a factor 1 over q square, which cancels this q square in the numerator. And then what one finds is that this integral depends solely on P1 squared. Single log, double log. and again a constant. And again terms of order epsilon, which we won't write down. And that's great because we are computing the collinear contribution and the answer depends only on the square of the collinear scale. P1 square, wonderful. That's exactly the way it should be. Okay. And again, we see double poles. Yeah, again of infrared origin because you see that you have 5 powers of k downstairs, 4 powers upstairs. So it's again infrared singularities of these integrals. Now, obviously, now we have also the third case where k is anticollinear. And here we don't need to do the calculation because all we need to do is to exchange P1 and P2 in this expression. It's completely symmetrical. So the anticollinear contribution is equal to the collinear contribution with a substitution that P1 square is replaced by P2 square. Sorry, P2 square. And now ideally, we would just add up. So sum them up. And we would expect to get back our finite result of the full theory, which was a log q square over P1 square times log q square over P2 square plus some constant. But surprisingly, that's not what we find. Well, for the moment, we haven't mentioned any soft pieces. That's not what we find at this point. Let me write down what we find if we add up the 3 terms. We find it goes wrong on all ends. Okay, so the double poles don't cancel. We end up with a minus 1 over epsilon square. The single poles also don't cancel. We end up with a bunch of logs, log mu square over q square, minus log mu square over P1 square, minus log mu square over P2 square, and then a bunch of double logs. Nothing is nice here. It's just a huge mess. P square minus 1/2 log square mu square over P1 square minus 1/2 log mu square over P2 square and the constant which is pi square over 6 plus terms of order epsilon. So this does not reproduce the full result, which is not uncommon when you use the method of regions. What does it mean? Well, if we trust this theorem by Smirnov, it simply means we forgot another topology, another region in the sum. So we are missing, one region, or at least one region. Okay. This is why I said that building an effective theory just of collinear and anticollinear particles will not work, will not be the full story. Just integrating out the hard stuff and working with collinear and anticollinear is not the full story. So at this point, of course, now you can say, well, what now? Now you can go back to the original integral and you can try to think of other regions that you could test. Actually, there's software. There's software packages. You give a loop integral, you give external momenta with certain scalings, and what they do is simply they parameterize k as lambda to the a, lambda to the b, lambda to the c with arbitrary exponents, and then they generate a million configurations and count whether this integral can have a leading contribution, and then they tell you, well, this is the regions I found. So this is one way of approaching, but we're going to use a somewhat more pedestrian way. There's two ways you can try to find what's going on. One way is to look carefully at this result, assuming that we didn't do a mistake, which we didn't. Let's look here, because if we found a new region, okay, it would correspond to some momentum scaling. And presumably this missing region that we are looking for, it will give us a 1 over epsilon square pole, which should cancel this guy. And then it will give us a 1 over epsilon pole, which should cancel the combination of logs that's standing here. Now these three logs we can combine. We can combine the terms in this first line as minus 1 over epsilon square minus 1. Let me write it as minus 1 over epsilon log mu square divided by something. And if I do that, the something that I need to divide by is P1 square, P2 square divided by Q square. Okay? Essentially, if I want to pull out a minus sign, so P1 square is in the numerator, P2 square is in the denominator, and Q square is in the numerator when I pull out a minus sign, which is the same as putting it here in the form of a double fraction. Okay, now what is this scale? If you do the power counting, this scale is lambda to the 4 Q square. So this is a scale which is smaller than Q square, not by 2 powers of lambda, but by 4 powers of lambda. That's peculiar. Okay. So this is much less than the collinear scale. The collinear scale, which was lambda square Q square. Now, there's also a physics argument which suggests that we need another mode. Imagine if we had an EFT which would just contain, let's say, which was just contain collinear particles belonging to one jet and anti-collinear particles belonging to the second jet. And hard particles, but we have integrated them out, okay? Now we can ask ourselves, what would possible interactions between these two sectors look like? Okay? If we had a field talking to the two sectors somehow, now if we wanted interactions between the two sectors, let's imagine we have a new particle X that couples to some collinear particle and to some anti-collinear particle. Okay, it doesn't matter now whether it's quarks or scalar fields. Let's imagine we had such an interaction with some field X. We see that there is a problem because the collinear particles have momenta scaling like lambda square 1 lambda. The anticollinear particles have momenta scaling like 1 lambda square lambda. In such an interaction, the X particle, by momentum conservation, the X particle would have to have the sum of the two momenta. But the sum of the two momenta, we would add a lambda square term with an order 1 term, so we get an order 1 term. In the second component, we would add this order 1 term with a small lambda square. We would also get an order 1 term. And in the perp component, we would get lambda. Okay? But this means px square. Remember, when we square a vector, we need to multiply the two light components and then square the perp component. We would find that px square is of order q square, which would mean it's a hard particle. But hard particles are not allowed in the effective theory. So in other words, if we tried to build a theory only of collinear fields and anticollinear fields, they would not interact. It would not be possible to have interactions between them. Now you can say, well, isn't that great? So I produce two jets and they don't interact with each other. That's wonderful. I have complete factorization. But you can see that there is a problem, because what are these jets? It's a quark and an antiquark. These are colored particles. At the end of the room, you have detectors. They don't measure quarks, okay? They measure pions. So somehow, you know, these quark, antiquark, they fly apart, but sooner or later they say, wait a second, I'm colored, I need to do something, I need to get rid of my color. Okay, so they need to exchange gluons between the two jets to neutralize the color. So there has to be an interaction. For physics reasons, there has to be an interaction. Otherwise, we would see colored quarks in the detector. But the direction cannot be a direct coupling between the two fields. So actually, we need something like in dark matter, where we have, you know, the standard model and the dark sector, and we need a particle mediating between our universe and the dark universe. So we need a third particle, a messenger. And this particle, you know, should interact with the collinear sector, and it should interact with the anticollinear sector. And as a messenger, it mediates interactions in that way between the collinear and the anticollinear sector. And that sector is called ultrasoft. So there should be a new region corresponding to ultrasoft particles which can interact at the same time with collinear particles and anticollinear particles. So that's the physics region why we should have another mode. And how are these ultrasoft particles built? Well, if an ultrasoft particle can interact with collinear particles, it means that if I take a collinear momentum and I add to it an ultrasoft momentum, this should stay a collinear momentum. It should not become something hard, like in this example here. The collinear is lambda square 1 lambda. So the ultrasoft has to be, you know, less than equal to lambda square, less than equal to 1, less than equal to lambda. I can do the same gain for the anticollinear. Here I get 1 lambda square lambda. And now the ultrasoft should be less than or equal to 1, less than or equal to lambda square, less than or equal to lambda. So these things combined tell me that the first component from here needs to scale at most of order lambda square. And the second component from here also needs to scale of order lambda square. The third component in principle could scale at order 1, but we want these particles, we want to define them in the Lagrangian as on-shell fields, okay? So if this is going to be an on-shell particle, the third component also must be order lambda square. Simply because, so this is the ultrasoft scaling at the end of the day. Times Q, simply because on-shell means this times this minus this square should be 0. So this has to have the same scaling on average. And you see that's great, because if we square this, P ultrasoft squared, we indeed get lambda to the 4 times Q square, which is exactly what we need to cancel this missing piece. Okay, so this is the picture. Picture is we have this ultrasoft sector, which needs to be there for two reasons. First of all, the best reason is physics. We need a mechanism to neutralize the color of two outgoing quarks. So some interaction needs to be possible, but this interaction is in exchange of an ultrasoft gluon. So I start running away in this direction. I say, oh my God, I'm colored, I need to do something, and I just emit, you know, my ultrasoft that, yeah, I knew I should not have done that the moment I let it go. But that was a hard impact, but it was an ultrasoft gluon, believe it or not. So, Not hard, collinear. Everything within the jet is collinear. Oh yes, the heart was, the heart was exactly this. You know, when I have a gluon exchange between the two jets, it needs to be hard. That was the hard contribution. That's the hard contribution. But the hard contribution will integrate out. It will become a Wilson coefficient at the end of the day. So within one jet, there's nothing hard. You cannot make a hard scale. Only within two jets, yes, there's a hard scale, and that was our hard contribution. Okay, great, wonderful. We found it. So now let's get to calculate this ultra-soft contribution. So this is the fourth contribution, K ultra-soft. Which means lambda square, lambda square, lambda square scaling. And now we need to again simplify the propagators. So K plus P1 squared is K square plus N dot K N bar dot P1 plus N bar dot K N plus P1 plus 2 K perp P1 perp plus P1 squared. So now K squared lambda to 4. Excellent. Lambda to the 4. N dot K lambda 2, I heard, so lambda squared, yeah, from here. N bar dot P1 is the big component, is order 1. N bar dot K, lambda squared. N dot P1, lambda squared, excellent. K perp, lambda squared. P1 perp, lambda, and P1 squared, lambda squared. Wonderful. You learned something very fast. So this can go, this can go, this can go. What remains is N dot K N bar dot P1 plus P1 squared. Which I can write, by the way, as 2K dot P1 minus plus P1 squared. And K plus P2 is completely symmetric. This is 2K dot P2 plus P2 squared. So now the ultra-soft integral is an integral with two linear propagators. K square plus I0. By the way, you never expand K square because no matter what the scaling is, this, you know, the scaling of K square is always homogeneous. You will never have something to expand out there. But for the remaining ones, yes, we get linear propagators. K times P1 minus plus P squared, P1 squared plus I0 and 2K dot P2 plus P2 square plus I0 and Q square upstairs. Again, what are the invariants that we can form in this integral? Obviously, we have P1 square. We also have P2 square. We also have P1, P2, but only in the form of P1 minus times P2 plus, which is 1/2 Q square. So this integral can depend on P1 square and P2 square and Q square, all three of them. But of course, only in a combination that corresponds to the ultra-soft scale. And that's exactly what one finds. You do this integral, you get, again, gamma function here, and then 1 over epsilon square with a plus now, plus 1 over epsilon, and now log mu square divided by, and exactly p1 prime square, p2 prime square times q square, plus 1/2 log square mu square q square over p1 prime square p2 prime square plus pi square over 6 plus order epsilon. And now if you add this here, you see that the miracle happens. You see that the epsilon pole squared cancels. You see that the single pole cancels, because we indeed get exactly this combination that we need. So I don't know, if you allow me to add the ultrasoft here, then the first term cancels out, the second term cancels out, and here we add an extra term, which is 1/2 log square mu square q square over p1 square p2 square, and also a pi square over 6. And then the order epsilon terms, now there are no poles, so we can set epsilon to 0. And now all you need to do is you need to hit full simplify. Basically, you need to decompose this log into logs of q and p1 and p2 and simplify this sum of double logs. And what you find is that you get, for the sum of all contributions, ultrasoft, you get 1/2 log q square over p1 square log q square over p2 square plus pi square over 3, which is exactly the result of the full theory. And it's a little bit of a miracle in a way, because the way the logs conspire is very non-trivial. And by the way, it's a simple matter to convince yourself. You know, let me back up a step. If you do a simple one-loop calculation, let's say an integral with two masses that are very different, one large mass, one small mass, at one loop, right? Typically, you get some alpha s over 4 pi, and then you get a log. In the limit where one mass is much bigger than the other, you get a single log. Say something like that, okay? And that's your one-loop correction, and at tree level, you get 1. So this is a typical calculation that we can do in QCD, plus some constants, okay? And now, you know, when you have a single log, it's very easy to rewrite this result. So typically, we rewrite this result in the following way. We write it as alpha over 4 pi. I'm leaving out coefficients here, of course. And now we could write this as log of minus log of mu square over m square plus some constant c1 times 1 plus alpha over 4 pi log of mu square over little m square plus another constant, right? And now we would say, this is a Wilson coefficient in the effective theory, which depends on the hard scale of the problem. And this is somehow the matrix element of an operator in the effective theory, which depends on the small masses of the theory. That's like SMEFT, for example, okay, where this would be This would be some BSM model, and now you split it up into a Wilson coefficient and a matrix element of some Smith operator. So the small scales are here, the large scales are there. And you see that this works because of the trivial identity that log m square over m square can be written as minus log mu square over m square plus log mu square over little m square. Just the addition theorem for logs. So mu here enters as an artificial separator, right? You have two scales which are far apart, and you introduce a line here, mu square, and you say, okay, from here to here, it's my Wilson coefficient, and from here to here, it's my matrix element. And that this works so nicely is due to this simple identity that you can split up a log of a product of numbers into a sum of logs. If you try to do this with a double log, so just take a double log of this type and try to write it as a sum of double logs depending on a single scale only, you will find that it's mathematically impossible with two terms. You cannot do it in this form. I mean, obviously, squaring this would not work, but it also wouldn't work if you allow for single log powers of these ratios. So basically, if you want to factorize a double log, and that's exactly what we do here, we have a double log and we want to factorize it, decompose it into a sum of logs depending on a single scale only, we need three scales. We need this scale and this scale and this scale, but also we need this ultra soft scale. This is completely true. If you want to so decomposing double logs into single scale objects always requires three scales. Three correlated scales. This is very important. In our problem, we have the scale q square here, so this is a log of the energy. We have q square here, which is the hard scale. We have the collinear scale, and if I said, let me just call it p square. We had p1 square and p2 square, but basically, let me say p1 square is approximately of the same order as p2 square. We could have set them equal from the beginning. So this was the collinear scale or the anti-collinear scale. But now we need a third scale, and the third scale is the geometric mean. So it's this scale squared divided by that. So p to the 4 over q square. Or if you wish, p1 square, p2 square over q square. That's the ultra soft. And it's like in the seesaw mechanism, right? You have your large Majorana mass, the Dirac masses, and then the physical neutrino masses are exactly this relation. And on a log scale, these distances are the same. That's what I mean by correlated scales. If you make these scales further apart, these scales automatically also go further apart by the same distance on a log scale. And that's absolutely crucial. Any sket has to have something of that order. You need three scales to factorize a double log, basically. And another point that is worth mentioning here is that this ultra-soft scale is a physical scale. This is not something mathematical that appears in the effective theory. This is a physical scale. And when you ask yourself, under what conditions can I calculate a jet process in QCD perturbatively? You may think that it's enough that the invariant mass of the jet is perturbative, so let's say 10 GeV or 5 GeV, much bigger than lambda QCD. But that's not enough. That's not enough. You must have the condition that, so that means this implies that we need the condition that mj to the 4 over root s is much, much bigger than lambda QCD squared for the process to be perturbatively calculable. And this is a bit counterintuitive. Normally you would think, well, I have two scales, the center of mass energy and my scat mass, my jet mass. As long as my jet mass is sufficiently large, just go ahead and calculate. But it's not true, because hiddenly the theory generates this ultra-soft scale. And if you want to trust your perturbation theory, you get logs of this ultra-soft scale. You saw them here. And if these logs are not in the perturbative region, then we need to introduce the concept of a non-perturbative soft function. Then the process is defined as some, hard functions, some calculable jet functions, but then convoluted with some non-perturbative soft function. And this is, sometimes people forget this because you cannot be aware of this, and then you think it's enough that the jet mass is in the perturbative domain. It's not sufficient. It's not a disaster if it's non-perturbative. It just means, scat gives you then a well-defined soft function. You can write it down. It's well-defined, but it's non-perturbative. You have to extract it from data somehow. In which integral? No, I added here. No, that was my red. I said, please allow me to add it here. This was the ultra-soft contribution from here. Oh, lambda, lambda, lambda. No, it's not a region. You can convince yourself. Well, lambda, lambda, lambda would be completely useless because it's not allowed to add with the collinear. You see, if I added lambda, lambda, lambda here, I would take a collinear, interact with it, and it would not be a collinear anymore. It would be. You can test it. Just go back to the original integral and now go to the region where k is lambda, 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 do the Taylor expansions, you will get a scaleless integral. Simply get 0, brute force, very straightforward. This is why I said they're packages. They do nothing. They take the propagators, they do the Taylor expansion in a region that you tell them, and then they tell you, do I get a leading contribution or not? And if all the integrals are 1 over k square or 1 over k dot p without anything that makes the integral scale full, simply scaleless. Yeah, exactly. So you would, it is not there. And if you want to convince yourself that it's not there, assume it's there, perform the Taylor expansion, and you will find it's a scaleless integral. And you don't get a region. Yes. Yes. The situation, this is the simplest version of SCAT that I'm discussing here. There is another version of SCAT called SCAT2. Sometimes this is relevant if you have particles with masses, for instance, electroweak gauge bosons. Again, Anish did nice work on SCAT in the context of massive electroweak gauge bosons. In that case, you can be in a situation where there can be some communication between soft, not ultra-soft modes and collinear ones, but not through direct interaction to an effect that is called rapidity divergence or collinear anomaly. But let's not go in this direction because we still have a lot to cover for this basic version of SCAT, which is called SCAT1 sometimes. So in that notation, the soft ones are called ultra-soft. The literature is not homogeneous on this. So sometimes instead of ultra-soft, people use you name soft here, and instead of collinear, the name hard collinear. And this is just a different vocabulary, so to speak. So you can have either hard collinear and soft, or collinear and ultra soft. But the scaling is always, it's always this picture, basically. 3 scales that are hierarchically separated from each other. Okay, so this was the motivation, if you wish. Now we want to go toward constructing an effective Lagrangian for SCAD. And we kind of know what the ingredients should be. We can have collinear fields. So basically what I want to do here, I want to have an effective theory containing collinear fields, anti-collinear fields, and ultra-soft fields. Now, which fields? Well, quarks, gluons, in principle, ghost fields. We're not going to write down the ghost fields, but remember they are there, of course, when you quantize non-abelian gauge theories. And we'll do this again in a very pedestrian way. So when we think about the interactions allowed by momentum conservation, where's my line? There, okay. We can ask ourselves what is allowed and what is not allowed, okay? So what is allowed is, for instance, I will just use phi, like a scalar field now, to represent any type of field. Gluon, quark, ghost, doesn't matter. I can have an interaction where I have a certain number of collinear fields interacting with a certain number of ultra-soft fields. That's this link in my diagram. You can have collinear fields interacting with ultra-soft fields. That is allowed, this interaction. However, momentum conservation, remember that if I have a bunch of ultra-soft fields, they will have momentum lambda square, lambda square, lambda square. If I have a single collinear field, it would have momentum lambda square 1 lambda. That would not be allowed. That cannot add up to 0 momentum. But if I have at least 2 collinear fields, so n bigger than 2, then it's okay. Then I can cancel the collinear momentum in that sum, and then I can add the sum of ultra-soft momenta. So I can have, at least 2 collinear fields and an arbitrary number of ultra-soft fields, 1 or more, that's okay. And I can have the same thing in the anti-collinear sector. I'm not going to write it down. What I cannot have, and I'm just repeating what we said before, I cannot have a bunch of collinear fields and a bunch of anti-collinear fields and a bunch of ultra-soft fields. Bigger than 1, bigger than 1, bigger than 0. This is not allowed because generically, if I have this bunch of collinear fields, I will get a collinear momentum here. Here I will get an anti-collinear momentum. Generically, these two together will make a hard momentum. This is a hard interaction. And since it's a hard interaction, it's already integrated out. It's not allowed in the low energy theory. And I can also not have a single collinear field with a bunch of ultra-soft fields. It's also not allowed because, again, this collinear field will have a momentum with a large component which I cannot cancel by adding a bunch of ultra-soft fields. So basically what I'm saying here is that the theory has this structure. There are interactions allowed between these two sectors, but not directly here. So this implies that the effective Lagrangian of SCET, it will have the following form. It will be a collinear Lagrangian, an ultra-soft Lagrangian, and an anticollinear Lagrangian. And then interaction terms, collinear plus ultrasoft and anticollinear plus ultrasoft. And because of this structure, it's sufficient if we analyze these three terms, because the anticollinear Lagrangian will be identical to the collinear one, and this anticollinear plus ultrasoft will be identical to this one. Okay, so I'm going to focus on the collinear Lagrangian and its interaction with ultrasoft. And then it would carry over identically to the case of anticollinear fields. So I'm going to start with collinear fields. And I'm going to start with collinear quarks. And this is now analogous, very analogous to heavy quark effective theory, as you will see. So basically, I want to simplify the Dirac theory of a collinear quark by using the same trick, by taking the four-component Dirac spinor of such a field and basically using the fact that in the large energy limit, two components of such a spinor, if it's on shell, are sent to zero, two components remain large. So I'm going to describe it by an effective two-component spinor. So the spinor of a highly energetic particle satisfies, well, actually, an on-shell spinor of a quark satisfies P slash equal to M times the spinor. But now for a collinear particle, M is much, much less than the energy, which is the zero component of the momentum, which is approximately equal to the three component of the momentum. And if you remember how we decomposed the momentum, if I insert the light cone decomposition of P mu, and I find that this is n slash over 2 times n bar dot P plus n bar slash over 2 times n dot P plus P perp slash. And this is the thing that counts like order 1, this counts like order lambda square, this counts like order lambda, and the mass term also counts like order lambda. So you see that in the limit where lambda is very, very small, this reduces to the equation that n bar dot P over 2 times n slash u of P is approximately equal to 0. I'm just keeping the leading term only. And once it's 0, I can forget about this factor, right? So basically, for a highly boosted particle on shell, the condition is that n slash acting on the spinor is approximately 0. Up to order lambda terms. So basically, you know, in the case of HQET, the corresponding equation was V slash acting on the spinor is approximately equal to M times, no, is approximately equal to the spinor itself. So we constructed a projection where V slash is kind of an eigenvector. So we'll do the same thing here. We'll introduce projection operators. we'll introduce projection operators Pn, defined as n slash n bar slash over 4. And Pn bar, defined as n bar slash n slash over 4. And these are projection operators in the sense that, first of all, Pn plus Pn bar is n slash n bar slash plus n bar slash n slash over 4. This is the anti-commutator in the numerator, so this is 2 n times n bar over 4, which is 1. So the sum of the two projectors spans the whole space, and Pn squared is equal to n slash n bar slash n slash n bar slash over 4 over 16. You can now commute this n slash through, then it hits the other n slash, that gives 0. So we only get the commutator term, so we get n slash n bar slash times 2 n bar over 16. N bar is 2. 2 times 2 over 16 is 1 over 4, which gives you back Pn. So Pn squared is Pn. It's good for a projector, and the last thing we need to prove is that Pn times Pn bar is 0. But that's obvious because that's n slash n bar slash times n bar slash n slash over 16. And n bar slash is proportional to n bar squared, which is 0. Okay, so these are two projectors. Yesterday I had 1 plus v slash over 2 and 1 minus v slash over 2 as my two projectors. Here it's these two projectors. They look a bit more complicated, but they are not at all more complicated. Okay, so we now define new spinors. So we define Cn as Pn acting on the quark field psi. And the quark field psi, yeah. If you wish, you can put a subscript C here, which means that this field contains the collinear momentum modes. If you take the full quantum field, psi of x, of course, in momentum space, it contains an integral over all momenta because a particle created by that field could carry any momentum. That's true. If you want to describe a collinear field, we can imagine, again, that in the mode decomposition in momentum space, we put a box around the region where this momentum is collinear. Okay, in the same sense that yesterday I said the effective heavy quark field is soft. It only describes soft fluctuations around the mass shell. In practice, you never need to impose this. Dimensional regularization does this automatically. But if you wish, what this means is take the full quark field, restrict it to collinear momenta, and now project out, apply this projection operator, and that's what we call Cn. And the other projection I will call eta. Eta n will be Pn bar times the full QCD quark field. Okay? Now, obviously, so here we don't pull out a phase factor like in HQT. We don't need to do that. Here, the full field is just written as a sum of two terms, C plus eta, where n slash acting on Xi is 0, because that's what Pn does, no? Pn is the projector, that if I multiply it with n slash from the left, it obviously vanishes. And Pn bar, if I multiply it with n bar slash from the left, it also vanishes. So this is an identity. I take the full field, I split it up into two spinors. The first one is annihilated by n slash. The second one is annihilated by n bar slash. And of course, the first one is going to be the good guy, because we know that you really exercise here during these lectures, working the blackboard. We know that in the high energy limit, the spinor should approximately satisfy n slash acting on it equals 0. Xi does satisfy that exactly, okay? So we will use Xi as a good interpolating field for a collinear particle because it has the same quantum numbers as the original field, and it satisfies, you know, the original field approximately satisfies this equation, Xi satisfies this exactly. So it's a good interpolating field. This would be not a good interpolating field. If I multiply this with n slash, I don't get 0. So this would not be a good idea. Xi is a good idea. But it will be the same logic as yesterday. We'll solve for eta in terms of Xi. So we're not going to neglect it. We're just going to integrate it out. Okay. I forgot when I started. I need maybe 2 or 3 minutes to finish. I think it's okay, right? Because I want to do the power counting for these fields, and then we're done for today. So let's derive the power counting. We know, of course, for the original field, if we look at the free propagator in the same way we did yesterday, just the Dirac propagator for collinear fields in full QCD. This is just the Dirac propagator, so d4p over 2 pi to the fourth e to the minus ipx, and now p slash, actually I'm setting the mass to 0 here. It wouldn't change anything if we added the mass term. So let's set m equals 0. This is the Dirac propagator, and you know, p square is order lambda square. P to the 4 is lambda to the 4. P slash here we can decompose in light cone components. It's a collinear particle. So depending on which component we look at, n dot p is order p square and bar dot p is order 1. P perp is order lambda. Okay, so I can now take this expression and multiply from the left and the right with Pn or Pn bar, and then I can get the corresponding expressions for Xi and eta. And what you find is that the 2-point function of two Xi fields is d4p 2 pi to the 4 e to the ipx. And now here I get n bar dot p over p square plus I epsilon times n slash over 2. And now you see we get lambda to the 4, we get lambda squared in the denominator here, we get a term of order 1 in the numerator, so this scales like lambda square. Okay. And now let me just be brief here. So if we take two eta fields, everything here is the same, except that here now we get n dot p over p square and n bar slash over 2. And this now, because of the extra n dot p, scales like lambda to the 4. And if we do the mixed ones, so for instance, one xi and one eta, you get the integral 2 pi to the fourth e to the minus ipx. And then here now p perp mu times pn gamma mu pn bar, and this scales like order lambda cubed, okay? And these scalings are all consistent, and what you find is that Cn scales like order lambda, and eta n scales like order lambda squared, okay? Two xi's make lambda squared, two etas make lambda to the 4, and the mixed term is lambda cubed. And that's the power counting of collinear quarks in SCET. And this is not the canonical dimension, okay? These are fermion fields. They have mass dimension 3/2. In HQET, the soft quark field was lambda to the 3/2. Here it's neither of the two is. But in particular, the leading one is lambda. You'll see that this one is power suppressed. That's why we can integrate it out. It will be a power correction. The leading one is lambda. So this is not the naive scaling. And I think, Anish, you also discussed the Weinberg rule this morning, right? For the chiral Lagrangian, which is also not the naive scaling. So you see an example here where the power counting is non-trivial in that regard. It's trivial to derive from the propagator. That's not the thing, but it's not just the canonical scaling behavior. So this is almost the most complicated part. With this result, we'll construct tomorrow the Dirac-Lagrangian, the coupling to gluons, etc., the whole machinery that we have. But it will not be difficult from here to get to the form of the SCET Lagrangian. But that will be part of tomorrow's lecture. Good. So, and let me remind you that I put a homework set online. You will find it linked right next to my lecture, to this lecture, to the second lecture. There's an extra file linked. There are 3 exercises. I already mentioned what they are, so feel free to have a look at it. Before leaving the school, I will also upload solutions, but you know, you are serious students, so you want to solve the problem before I upload the solutions. If you have a problem, then you can look at the solutions.
Before the solutions are released,